The first problem that we look at in calculus is the tangent line problem. And that means that, say, we have a curve, and here's a point here. A tangent line is a line that, a line that is tangent to a curve is one that touches it in one place, and there again shall it touch. Okay. And don't be confused, as I'm drawing this, I'm only talking about this area. If I did draw this line more, it would cross a quote second time. But that's way over here. We're talking about right here at this point. Okay? It could even cross again near here, but we're talking about locally at this very point. If this thing came down, let's say, for example, that this went down a little bit for a second and went back up, and I wanted to find the tangent here, it'll cross right here, it'll touch right there, and yeah, it does touch it again there, but if we were to zoom way in here, we would find that at this very spot, locally, it only touches it once. And this will be more clear as we go on. Anyway, that's a tangent line. A line that touches only once in that local area. And then we talk about the derivative of a function. And that really has no meaning yet, but it will soon. Okay, so let's get a bigger screen to work with. Here's some curve. And say at this point right here, I'm going to know the tangent. I'm going to start asking questions about the tangent line at this point. So please excuse how awful this looks. The main question that I want to know, because let me explain why I'm about to ask this question. Let's say that, as odd as it would be, this is a map or a graph of a trip that we took. This would be the distance that we traveled, and this would be the time that it took us. So I don't know what kind of trip we would take that would do this. Maybe we have like a delivery route or something, and we go out in the morning and deliver all our stuff and get far away from home base. We get our stuff, and then we go out and we get the farthest away that we get, and then we come back, and I don't know, maybe there's some other distribution center that's really close to this one, and then we pick up our stuff and we go off again. I don't know, something like that. The question, though, is what's the slope of the tangent line at this point? And the reason why is because the slope, the rise over the run, the distance versus the time would at that point be our velocity. If we had a graph that was like this, just straight lines, then that would be easy to interpret. We could look at this. We've traveled this distance vertically, this distance over this horizontal amount of time. So we take the slope of this line and we know our average velocity over the entire trip, or over this leg of the trip. And then we can see as the slope decreases, we are slowing down. And as we come over here, we see maybe we took a nap because we were getting tired. And then we took off again, and we were going pretty fast because it's a pretty steep slope, right? And at any instant, we're just going the same velocity here. Nothing's changing. So at any instant, we could know our velocity. But when it's curved like this, how can we know our velocity at any instant? And that's the question. So I'm going to take those away and talk about this tangent line. I'm going to get another color here. Right. this is the point where I want to know the slope of the tangent line, because I want to know how fast I was going at that point. That's one problem that knowing the slope would solve. Uh, well, what we I mean, how do you do that? We define the slope as the rise over the run. So I need 2 points and say I went up this far and over this far, and that's the slope. But we only have 1 point that we know of for the tangent line. And so how do we find the slope? We need a second point. So let's go ahead and give ourselves a second point. And draw a line through it. Now this is not a tangent line, is it? You see how this guy here differs from this, I don't know, what is this, fuchsia? Is that fuchsia? It's a pinky color, and they're different because this green one just touches it at one point, this one crosses over it. So just to help you understand what a tangent line is still a little more. Now we have 2 points. Okay, so let's look back at this point they originally wanted to know about. We'll call it C. You know, C is the x value. We wanted to know the slope of the graph at this point C. But we had, now we're starting to think, what if we gave ourselves a second point? Because usually we need a second point for a slope. Usually the slope m is y2 minus y1 over x2 minus x1. That is the equation for a slope. So now we kind of have that. We have an x1, y1, x2, y2. Okay, so we could fill those in. And this is just kind of a thought. Maybe this is going to work. Here's this other x that's out here. And it relates to this other y here. Yeah, we could do this. Let's call this point here is clearly it's C, and if this function we have here is f, then this would be f of c. That'd be our output, our y value, and this one we could call x, f of x. Okay, now our slope could become this. F of x minus f of c over where would be x minus c. We could do that. And that is one way to talk about the slope. What we're going to do in order to be able to find the slope is to define it a little bit differently. Rather than giving this guy its own name, x, right? That would be the name that we gave it. We're going to talk about c and then the distance between c and x. Okay? Well, that would just be, this distance here. The distance between c and x. And if we're talking about the slope of this line, then this bit here would be, for these 2 points, delta x, the change in x, the change in y over the change in x. This would be the change in x. Delta x, that's what delta x means, change in x. Okay, so now what happens to this point? It becomes redefined. Rather than x, we could say it's c plus a little bit more plus that delta x. And then f of x would become f of c plus delta x. Okay, that might look a little weird, but it's going to clean this slope up a little bit. So now it becomes f of c plus delta x minus f of c, change in y, right? Here's this y value of this point is f of c plus delta x, y2, minus f of c, that's down here, that's this y1, okay, y1 minus y1, over, now we could say x2, that's c plus delta x minus x, so x2 minus x1 minus c. But look what happens with our c's. We get a c minus a c, so they're gone, right? And this makes sense because this is the change in x. Change in y over the change in x. That's what delta x is by definition, is the change in x. Okay, good. So we've got this thing defined. This is the slope of the tangent line. Well, it's the slope of the secant line. But what happens if, instead of having such a big delta x here, such a big gap, what if we cut it down almost by half, or right out of half? Now look at this pinkish line and compare it to the green line. It's a much better approximation of the slope than this first one was. Move it even closer, and you got an even better one, and closer you get a better one, and a better one, and so on. Slightly better until you almost squeeze the two together. Squeeze this second point almost right on top of this point, okay? And this is where we use limits. That's why we've been doing limits. We want for this to become a very good and eventually an exact approximation, an exact value of the slope of the tangent line. We want this guy to go to 0, if that's possible. We want the limit as delta x approaches 0 of this whole thing. Over delta x. You see, that's the slope of the tangent line. If we could let delta x become 0, then we would have the slope, because there would be no gap, there would be no distance, no delta x between c and x, c and c plus delta x. Yeah, but there's the problem of delta x going to 0. We let delta x be substituted by 0, and we have this undefined fraction, right? And that won't stand. So let's see. Let's use that definition. Let's leave it up there, and we'll do y equals 2x plus 3, and we want to know the slope at. Let me take that away. Let's find out the slope of this line at x equals 5. Okay. So at x equals 5, that would be like our c. That's the point at which we want to know the slope of the tangent line to this graph. And we don't, delta x is this ambiguous thing, so it's not really a value that we need to worry about. So it's really like c is equal to 5, just to help ourselves out understanding. So we're looking at the limit as delta x approaches 0 of f of c plus delta x, so f of 5 plus delta x minus f of 5 over delta x. Okay, and here's where limits come in handy, because I can't just put delta x in there, but I can hopefully cancel this out, which we've done before, in order to get rid of that problem 0 value. So we find some function, right? Some new function that agrees with this function at all but one point, and we have a limit that will tell us what we want to know. It'll tell us the value of this as delta x goes to 0. So let's figure this out a bit. Limit as delta x approaches 0 of, well, what's f of 5 plus delta x? Well, that means take 5 plus delta x and put it into this function, so that's 2 times 5 plus delta x plus 3. That's that first part. That's f of 5 plus delta x minus f of 5. What's f of 5? We'll put 5 in here. 5 times 2 is 10 plus 3, 13 over delta x. Okay, let's take it up here. Distribute the 2. 10 plus 2 delta x plus 3 minus 13 over delta x. Hopefully we can see 10 plus 3 is going to be 13, minus 13 is going to be 0. So really what we have is the limit as delta x approaches 0 of 2 delta x over delta x. And look at that, delta x's they're just, it is a value, it's just one we don't have a number for, but they're going to cancel each other out. So what we're left with is, put 0 in for delta x, which there aren't anymore, and you have 2. So we're saying that 2 is the slope of the tangent line at 5. And that should be believable because this is a line. It has a slope. A line has a slope. And the slope at all points for this line is going to be 2 if we recognize that this is y equals mx plus b. It's slope-intercept form. The slope is 2. So of course the slope should come out to be 2. But hopefully we see the work done and we're convinced, oh, maybe this thing does give the slope of the tangent line. Okay. Let's try really quickly y equals x squared. Yeah, that's fine. So let's remember that we're looking at the limit as delta x approaches 0. F of x, let's see, f of c plus delta x minus f of c over delta x. So let's say I put in that x is 3. Where x is 3, I want to know the slope of this line, or this curve. And remember, this is a parabola, goes through the origin. It's supposed to go through the origin. And somewhere out here at 3, I want to go up on this thing and know the slope of the tangent line. That's what we're going to do. The limit as delta x approaches 0 of f of c plus delta x. So that's, let's call this f of x. F of x equals x squared. So c plus delta x, that would, f of c plus delta x would be 3, because now we're saying this is c. 3 plus delta x squared minus f of c, that would just be 3 squared all over delta x. The limit as delta x approaches 0 of foiling this out, 6 delta x plus delta x squared minus 9 over delta x. And so 9 minus 9, that's going to cancel out. Okay. And then if you'll notice, there's a delta x in all of these terms. I could factor a delta x out in the numerator. What's left of it? Delta x times 6 plus delta x over delta x. So these guys can cancel out. We have an equivalent limit of 6 plus delta x. Now substitute 0 for delta x, you're left with 6. And you could graph this in your graphing calculator. Convince yourself that at 3, the tangent line would have a slope of 6. It would go up 6 and over 1. Okay, so there you go. There's the slope of the tangent line. Now, let's talk about our number 2 thing, the derivative of a function. As you can see, I could have just as easily done 2 or 4 or 5 or whatever I wanted to do. I could put it in here. So what I'm going to suggest, and I'm just going to erase the solution here. We all remember it's 6. So I could have put anything in there. I could have put anything in there. X. X means, anything. So what we have now is, rather than putting in a 3, a number, I'm going to put in an x. So let's do this again, but c is now x. The limit as delta x approaches 0 of f of x plus delta x. So that's x plus delta x squared minus f of x, okay, but f of x is just x squared. It's given from the get-go, all over delta x. Okay, you can see I'm following right along with this. But rather than having a 3, I'm having an x. All of the math should be the same. The same things should cancel. You can see that this number is the same as this number, and it's getting squared in both cases, and that's what's canceling. And so I'm just going to do like all of the numbers possible all at once. 2x delta x plus delta x squared minus x squared. In the same way that the 9's canceled over here, x squared is going to cancel with negative x squared. We're going to factor out a delta x in the numerator. We're going to cancel out these delta x's, and we get this limit, as delta x approaches 0, of 2x plus delta x. Substitute a 0 in for delta x, and we're left with 2x. What's the significance of this? Over here it came out to be 6, and 6 was the slope of the tangent line of this graph at 3. Over here, this is the slope of the tangent line of this graph at anything. Any x that I want to put in here, I can find the slope. That is awesome to me. You have a new function that directly relates to this function, such that anywhere you want to know the slope, whether it be 0 or 1 or 3 or a billion, it doesn't matter, I now can find the slope of the tangent line at that point. So if it just so happened that this described my distance over time, if this was the graph of a trip I was taking, which I would be accelerating really quickly, getting really steep, and we know that steepness translates to fastness. I'm traveling a great distance over a relatively short amount of time, which means I'm going quickly. And at any point that I'm curious about what my speed would be, I just plug in that, in this case it would be a time 1, 2, 3, 4, 100, and it tells me my velocity, my slope. So that is what we call the derivative. The derivative is a function itself, and that function, that derivative, tells us the slope of the original function at any x value we want. And if that doesn't blow you away, I have little else to show you that's that amazing. So I hope that was helpful. We'll do some practice problems. I'll see you there.